What you're seeing is Backprop learning from the data, and it's a spectacle of intelligence in action. Magical. The monolith algorithm that has made all this possible is backpropagation. Everyone in AI adores backpropagation.
Adorable!
However, this affection comes with its own set of challenges. Need for differentiable activation functions, exploding gradients, vanishing gradients, the computational intensity, saddle point issues, sequential nature limiting the perfectly parallel computation, and many more. Before we dive deeper, which of these do you think possess the biggest challenge to backpropagation? Comment below. But it still works, right? Why? For that, gotta understand backpropagation. Starting with a naive example, I give you a guitar, and you have to ensure every string is tuned. How do you do that? You can use a tuning device that listens to each string's sound and compares it to the correct frequency for that string. You adjust the tension of each string accordingly by tightening or loosening until the pitch matches the desired note perfectly. Similarly, backpropagation in a neural network involves adjusting the weights of the network's connections. In this process, the network makes a prediction, and the difference between the prediction and the actual target value, aka the error, is calculated using a loss function. This error is then propagated back through the network, layer by layer, adjusting the weights as it goes to minimize this loss, effectively tuning the neural network to respond correctly to inputs with accurate predictions. That's all good, but where is the... Alright. For dummies like me, I'm starting with 2 input nodes, 2 hidden nodes with ReLU, and 2 output nodes with softmax activation, evaluated by cross entropy or log loss. Later, we will visualize it on a super cool image network. If this video is daunting, the ultra basics is explained in a previous video, go have a look. The output Y in a matrix form in the forward pass here is softmax of ReLU of weight at layer 1 times the input again ReLU weights. You know what I mean. For backprop, we need the derivatives of loss for our weights, technically also with respect to biases. Since we're dealing with dummies, I leave it out. In case you want to feel like an AI geek, bias will just get added to the product of input/activated neurons and the corresponding weight layer. Calculating all the local derivatives gives us the derivative of every operation with respect to the one right behind it. These local derivatives are then coupled according to the normal or multivariate chain rule to give global derivatives numerically. For instance, this is how you get the derivative of loss with weights in layer 2 and extend it a bit to get the derivative of the loss with weights of layer 1. Such calculations can be complicated.
But practice makes perfect.
The derivative of loss with weights, also biases, is fundamental to the gradient descent update rule, also explained in my previous video. This aids the model in finding better weights, giving us a better approximation of the actual probability distribution or a complex function responsible for generating the output for the given input. But practically no one works with 2 input nodes.
I do!
No, you don't. Anyways, for a small case, I'm working with the classic MNIST dataset of 8x8 pixels image, a handwritten datasets of digits from 0 to 9. Taking 64 input nodes, 1 for every input pixel, 12 hidden nodes, my favorite activation function, ReLU boy, and since the output can be anything from 0 to 9, 10 output nodes, activated by softmax. The architecture is ready. Notice that this network with no biases, risky but I'll go with it, has 888 weights, which are randomly initialized. For this instance, when I'm predicting an image of 8, the image gets broken down into a long vector of length 64 and goes into the network, passing through all the weights of layer 1, then layer 2, and giving a vector of length 10 consisting of the probability of it belonging to a particular class. The gradients are then sent back, and for multiple batch inputs, an aggregation like mean is used to update the weights accordingly. And the issues begin. Since you're dealing with derivatives, of course you need differentiable functions. But do you?
No, I don't think so.
I agree. Maths always helps. If the outputs are normalized and you know for sure that it will fall in a definite boundary, let's say 0 to 1, then you can use it. You do not always have to go for differentiable functions. Take a quick one and just normalize smartly. But normalization does not completely solve the vanishing or exploding gradient problems. These issues arise when the network is deep and our chain rule squishes the local derivatives to 0 if the values are less than 1. Otherwise, it explodes. To limit the explosion, you can use gradient clipping or have a dynamic gradient penalizing mechanism. Use these and you'll be happy. Otherwise,
everything will explode.
exactly. But vanishing gradient is a bit difficult. Can't clip it, right? Everything will come 0. Therefore, you have to pick the activation function thoughtfully. Use a leaky ReLU or a normal ReLU. Please avoid sigmoid and tanh, especially for deep networks. These functions saturate quite quickly, unlike ReLU. And if not well normalized, will hit you back harder. The introduction of ReLU might increase the chances of exploding gradients, but believe me, vanishing ones are more painful.
I can understand.
We still need a lot of computation. How to deal with that? There's literally a million ways of doing this. I will stick to the advanced basics. Prune the model. Just delete the weights that are close to 0. Read some stuff first. It's not easy as it sounds, but insanely helpful. In one of my clients' mobile optimization projects, pruning decreased the weights by 38% and performance by just 2.8%. It works. Additionally, knowledge distillation helps, training a baby AI to behave like a daddy AI. Initially, it might be shitty, but works quite well. Other workarounds include using ReLU-like activation functions, it's fast, efficient architectures, avoiding stupid computational graph generation in PyTorch, and so on. The saddle point issues, don't worry about it. An adaptive learning rate should mathematically be enough, assuming you have enough data though, to move the gradient descent algorithm past saddle points. And finally, parallelism. Although inherently, a single run always happens on a single machine, but batches can run parallelly, right? In sync with the concepts of data parallelism, model parallelism, pipeline parallelism, or a hybrid approach. That's all the solutions that you got. Subscribe for more solutions like this.